Well, hello, ladies and gentlemen. So today we're going to continue on with our investigation and use of the open system energy balance, mass balance too. So I think it's a good point or a good time to actually go through and describe the various open system type devices or open flow type devices. These are turbines, compressors, nozzles, diffusers, heat exchangers, the various devices that involve the use of the open system conservation equations. So we're going to go over open system devices today and just list them and talk about what they do and how they work. And then we're going to spend the rest of the class doing an example or two involving the open system energy balance. Okay? So let's look at open system devices. Open system devices. The first broad category of open system devices are energy conversion devices. So energy conversion. For example, conversion of internal energy. So example, devices that convert internal energy to kinetic energy or vice versa. Those are nozzles and diffusers. So here we have a nozzle. So a nozzle is a device which focuses or restricts the flow in some way. So we have the inlet. So we have m dot in. And then we have flow coming out. And so you have a velocity here at the inlet. Usually slow moving fluid comes in at the inlet and fast moving fluid. So velocity at the outlet is moving fast relative to velocity at the inlet. So we're focusing the nozzle, increasing the velocity of the flow, increasing the speed of the flow. And how does it do that? How does it actually increase the speed of the flow? Well, it takes pressure work and to some extent internal energy, pressure work and internal energy, and converts it into kinetic energy. So usually the enthalpy at state 1, that's given at the inlet, and the enthalpy at state 2 is given at the outlet. Usually the outlet enthalpy is less than the inlet enthalpy. We're converting pressure work and internal energy into kinetic energy. The velocity of the flow at the outlet is greater than the velocity of the flow at the inlet. So we're increasing the kinetic energy of the flow across this device. This is called a nozzle. A nozzle, okay? So we have a nozzle. The opposite device, a device that converts kinetic energy into pressure work and internal energy, is called the diffuser. So here we have a small inlet and the flow gets expanded. So we have m dot in and we have the outflow. Usually we have an inlet velocity, so VEL in. And the inlet velocity is a lot greater than the outlet velocity. So the outlet velocity is less than the inlet velocity. We slow the flow down by the area change that you see here. Typically pressures go up and enthalpy goes up. Internal energy and enthalpy go up as we go from the inlet to the outlet. So we have an inlet enthalpy, H in, and we have an outlet enthalpy, H out, and the outlet enthalpy is usually greater than the inlet enthalpy. So we're taking kinetic energy, converting that kinetic energy partially into pressure, power, and internal energy. Enthalpy goes up as we move through this device. This device is called the diffuser. diffuser. And so the idea is we take kinetic energy and convert it into internal energy and pressure work. In other words, enthalpy goes up, okay? The nozzle does the opposite. We take internal energy and pressure work or pressure power, if you like, enthalpy, and we convert it into kinetic energy, okay? So these are energy conversion devices. Energy conversion devices. Nozzles increase the kinetic energy of the flow. Nozzles increase the kinetic energy of the flow, and diffusers decrease the kinetic energy of the flow. Okay? Now, these two devices, the nozzle and the diffuser, are no work devices. And what I mean by that, no boundary, no shaft, and no electric work. And the energy balance, the work term W dot is 0. Okay? There's no propellers, wires, or any deformation of the system. Okay? And the system in this case, of course, is the inside, the flow, the air or whatever material is going through the diffuser, that's our system. Okay? Now, what about work producing or consuming devices? There are devices that either produce work or consume work. Work producing or consuming devices. Work producing or consuming devices. The big one you should know about is a turbine. Turbine. A turbine produces work or power, okay? Turbine produces work or power. It takes enthalpy, in other words, internal energy and pressure power, and converts it into some kind of work. So here we have the inlet, and here we have the outlet of a turbine. So we have m dot, flow comes in, flow goes out. We have a enthalpy at the inlet, an enthalpy at the outlet. And the idea is the outlet enthalpy is usually less than the inlet enthalpy. So we're converting internal energy and pressure work into some kind of other power. In particular, we have a propeller in here, and it is producing W dot shaft. Okay? So we have some sort of propeller in there that's spinning, extracting energy from the flow and producing shaft power. Often these turbines are adiabatic. If they're insulated, they're adiabatic. So Q dot is usually 0, although not always, not always. So that's a work producing device. Typically, pressure at the inlet is greater than pressure at the outlet. Okay, pressure in is greater than pressure out. So we're converting pressure power and internal energy, in other words, enthalpy. We're converting enthalpy into some kind of a shaft work, okay? Then we've got compressor. Compressor. A compressor consumes power or work. It looks just like a turbine. We have an inlet, and we have an outlet. Oops. So we have an m dot, we have an h in, a p in, we have an h out, and a p out. And this thing has a propeller in it, or some kind of a rotating blade of some kind. And this thing consumes consumes shaft work. So W dot shaft, it consumes shaft work, and it does work, therefore, on the flow. So we're taking work, and we're resulting in an increase in pressure power and an increase in internal energy. So the outlet enthalpy is greater than the inlet enthalpy, and typically it results in a pressure rise. We're pressurizing or compressing the flow, so the outlet pressure is greater than the inlet pressure, okay? So a compressor pressurizes the flow, increases the pressure. As a result, increasing the enthalpy and internal energy of the flow, typically. A turbine, on the other hand, produces power or work, shaft power, and as a result, pressure falls across the turbine, and enthalpy and internal energy fall. Work-producing, work-consuming device, turbine, compressor. Typically, these compressors and turbines are adiabatic. In other words, we assume there's insulation wrapped around this device so that there's no heat transfer externally. So usually the Q dot term could be neglected when you do turbine and compressor problems. Same thing with diffusers, but not always. Sometimes you'll have a problem involving or a situation involving heat transfer for any one of these devices, and then you will have to re-examine the energy balance, okay? Work-producing, work-consuming energy conversion devices. We also have one last class of device that we're going to talk about here, and those are heat exchangers. So a heat exchanger transfers heat from one system to another, one open system to another. So we also have heat exchangers. Heat exchangers. So let's say we have a device that looks like the following. So we have a pipe here, and we have some sort of fluid moving in and out. So we have an M dot there, okay? Now this fluid comes in at some temperature, I don't know. I'll call it T in, and it leaves at some temperature T out. Now, why would the temperatures be different? Aside from the fact that maybe the flow is accelerating and maybe we're converting some of the internal into kinetic energy. Well, let's say we have another pipe here in which we're pumping a hot or a cold fluid. Okay, maybe this is a coolant of some kind, M dot coolant. So we have some sort of a cold fluid being piped in through this pipe. And because we have a cold pipe and maybe a warm material, there is a heat transfer from the warm material to the coolant. Okay, so we have some sort of material that we're trying to cool, and we're cooling it using some sort of a coolant. The coolant is cold, the material is hot. So in this case, presumably, T out is less than T in. So this would be some kind of a cooling or a chilling device that cools the main flow. Whatever this M dot is, it cools the main flow down using some sort of a coolant. So that's another device, heat exchanger. Let's go over this again. Energy conversion devices, devices that convert internal energy and pressure work into kinetic energy, nozzles and diffusers. And then we have work-consuming and producing devices. A turbine produces work by converting internal energy and pressure power into shaft power. A compressor does the opposite. You do shaft work, or you apply shaft power to a fluid in the compressor as it passes through, and it converts it into pressure work and internal energy. Heat exchanger transfers heat between two different fluids, okay? So these are some open, very common open flow devices. This encapsulates probably 95%, 99% of all the open flow or open system devices that are in existence, okay? Or a combination of these devices. All right, let's do some examples here. Let me cut this and we'll do an example. Okay, so what we have here is an air nozzle and an adiabatic air nozzle. So of course, an air nozzle takes pressure, power, and internal energy, in other words, enthalpy, and converts it into into kinetic energy. So we have slow moving air coming in on the right, on the left. So out here we have VEL1 equal to 50 meters per second. By the way, the pressure at the inlet is equal to 300 kPa. Okay, so we have incoming air with a certain velocity and pressure, and the air exits the nozzle. So the area is being reduced. Exits the nozzle, the pressure equal, so P2, that's at the exit, location 2, 100 kPa. And an outlet velocity, VEL2, of 320 meters per second. 320 meters per second. So the velocity is increased by over a factor of 6 between the inlet to the outlet of the nozzle, okay? So this nozzle is increasing the velocity of the flow. Now we're also given, besides that it's an adiabatic nozzle, we're given some temperatures here. The temperature at the inlet, T1 is 350 degrees Kelvin. All right, so we know the inlet temperature, pressure, velocity, and we know the outlet pressure and the outlet velocity. What are we supposed to find? We're supposed to find the outlet temperature, T2. So we're supposed to find the outlet temperature, T2. Presumably, we're going to be converting internal energy and pressure power into kinetic energy. So presumably, the temperature will fall, okay? Internal energy increases with temperature, so it goes down with decrease in temperature. So we should be cooling the air as we accelerate it to a higher velocity. Also, the inlet flow area, this flow area right here, this inlet flow area, area 1, is given at 0.01 meters squared. I want to know what the outlet flow area is. I want to know what area 2 is. How large does the outlet circular flow area have to be to accommodate the mass flow through the nozzle, okay? After all, pressure and temperature are going to be different from the inlet to the outlet. So density is going to be different, and velocities, of course, are different. So we're going to need different flow areas, and we'll see this when we do the calculation. Let's see here, assumptions. We'll write those as we go along, okay? All right, let's proceed to analysis here. So we want to find the outlet temperature for the airflow through our nozzle. We want to know what the outlet temperature is. We'll worry about the flow area later. So what's the outlet temperature? Well, if we knew some kind of property at the outlet, a specific enthalpy, an internal energy, and we assumed ideal gas behavior, it is air after all, we can probably assume ideal gas behavior, but maybe we should check to make sure that the temperatures and pressures give us a Z value, a compressibility factor close to 1. So if I know the enthalpy, specific enthalpy or internal energy at the outlet, I can back out from air tables what the temperature is, okay? So somehow I need to get the outlet enthalpy or an internal energy. So analysis. Well, clearly the equation which has enthalpies in it is the energy balance. So let's apply the energy balance to our nozzle and see what we get. E balance So what's the motivation here? The motivation is if I know an H or a U, I can get a temperature at the outlet. I know an H or a U, specific internal energy entropy, I can get a temperature from a table. Okay, so we need to get U or H. Let's apply the energy balance to our nozzle. Let's apply the energy balance to our nozzle. Let's define our system. Let's define our system here. So our system is going to be the area or volume inside of the nozzle, which contains our airflow. Okay? Notice that we have air flowing across the system boundary in two places, the exit and the inlet. So we got one inlet, one outlet. Okay, so let's write down the energy balance. Closed system or open system? We have an inlet and an outlet. It's going to have to be an open system energy balance. Q dot minus W dot is equal to dECV dt, time rate of change of energy within our nozzle, plus the sum of m dot H plus PE plus KE summed over all outlets, minus the same thing summed over all inlets. Okay? Let's go through each and every term in this energy balance to see what we can get rid of. First of all, we're told it's an adiabatic nozzle in the givens. So Q dot is equal to 0. 0, adiabatic. Okay, it's adiabatic nozzle. Let's go over here to our schematic. Let's go over here to our schematic and indicate that this is insulated. So I'm going to put some insulation around my nozzle. No heat transfer. It says it's adiabatic. Adiabatic means no heat transfer. Okay? Also, do we see any wires in here or shafts? Any wires or shafts or so if there's no wires or shaft, there's no shaft power or no electric power. Also, the nozzle isn't changing shape, presumably. So that means volume isn't changing shape. So that means no boundary work or power. So the entire work term is equal to 0. Evidently or apparently, okay? Okay, left-hand side is completely 0 now. What about the time rate of change of energy within our nozzle system? Well, if we assume steady state, we don't have to worry about the nozzle increasing or decreasing in the energy inside. And I can get rid of this term. So let me assume steady state operation. Nothing changes in time. It's a steady state problem. So steady state. So I'm going to assume steady state. I'll just put SS there, okay? No time rate of change in energy within the control volume. Okay, we have one inlet, one outlet. So let's write down what we have. One inlet, one outlet. Let's see, so this is m dot. So we got 0 equals m dot out, which is at location 2, H plus PE plus KE at location 2, minus m dot at the inlet, which is location 1, H plus PE plus KE at location 1, which is the inlet. So all that stuff, one subtracted from the other, is equal to 0. Let's see if we can whittle this away or whittle this down a little bit further. What's the relationship between the mass flow going in and the mass flow going out? M dot 1 and M dot 2. Single inlet, single outlet. steady state, that means m dot in has got to be equal to m dot out. Let's prove this. Let's apply the mass balance. Let's apply the mass balance to our nozzle so we can prove this. So we got mass balance. Time rate of change of mass within our control volume is equal to the sum of the inlet flows minus the sum of the outlet flows. That's mass balance or mass conservation for our nozzle. Steady state, so there's no change in mass inside of our nozzle over time, so that goes to 0. Single inlet, single outlet. The inlet is at location 1, so I have m dot 1, and the outlet is at location 2, so I have m dot 2. So this implies 0 equals m dot 1 minus m dot 2, which implies m dot 1 is equal to m dot 2. The inlet flow is equal to the outlet flow, so I'm just going to call them both m dot. The flows are the same. So both these m dots are the same. I'm just going to call them m dot now. They're the same. And I can divide both sides of the equation by m dot and cancel out the m dots. So now I'm just going to cancel them. Okay? Left-hand side is 0, so I can divide both sides of the equation by m dot. All right? Now the m dot's gone. Let's look at some of these terms inside here. So let's rewrite this equation. I'm going to group together the enthalpy terms, the potential, and the kinetic energy terms. So I have 0 equals H2 minus H1. So I'm grouping together the change in enthalpy, the H2 minus the H1. The m dot's gone, plus PE2 minus PE1, plus KE2 minus KE1, okay? I'm just grouping together the kinetic potential and enthalpy terms. This change in potential energy of the flow, this has to do with the average height of the flow or position of the flow. That nozzle there, we look back at the nozzle, the average height of the flow is not changing. The average height of the flow is not changing. And typically, as far as forces are concerned, changes in potential energy of something light like air, maybe not water, but certainly light with a low density like air, usually the change in potential energy terms are quite small. But in this case, there's no change in average height between the inlet and the outlet flow. So we're going to neglect the change in potential energy between the inlet and the outlet of the flow. So delta PE as the flow goes from the inlet to the outlet, I am going to set that equal to 0. Delta PE from 1 to 2 is equal to 0. That delta PE here, this is delta PE from 1 to 0. PE2 minus PE1. And I'm going to set that equal to 0. Okay? So this term is gone. All right? Now I want an outlet temperature, which means I really want an outlet enthalpy. Outlet enthalpy, specific enthalpy, if I get that numerically, I can go to an air table and back out a temperature. So let me solve this resulting equation for H2, the outlet specific enthalpy. So from our E-balance and application of conservation of mass, I have H2 is equal to H1, specific enthalpy. So I'm going to take the H1 and put it over here. I'm also going to take the KE2 minus KE1 minus KE2 minus KE1. I'll take this term and these terms, put them over on the other side of the equation, and then flip the whole equation. And I have H2 as a function of the inlet enthalpy and the change in kinetic energy of the flow. Now H1, specific enthalpy at state 1. Let's see if I can get that. So H1 is equal to the specific enthalpy of air evaluated at T1. Now, where do we go to get this? If I assume ideal gas behavior, maybe I better write that down. IGB. If I assume ideal gas behavior, I can go, now just give me a minute. Let me see if I can open up the notes here. Just give me a second. Okay. Okay, so page towards the end. Let's see if we can find IGB air property tables. Ideal gas saturation tables. Ideal gas properties of air: temperature, enthalpy. Okay, my inlet temperature, T1, is 350 degrees Kelvin. 350 degrees Kelvin, 350.49 is the specific enthalpy for my air, okay? 350.49. Okay, 350.49, there we go. All right, so we have H1. What about the change in kinetic energy of the flow, KE2 minus KE1? Well, KE2 is 1/2 velocity 2 squared, and KE1 is 1/2 velocity 1 squared. I have both these velocities, okay? I have both these velocities. So H1 minus, I'm going to factor out the 1/2, and then I have velocity 2 squared minus velocity 1 squared. Okay, and I have all this stuff. Let's plug in, let's get H2. Let's see here, 350 is my specific enthalpy at the inlet. And then I have minus 1/2 outlet velocity. Outlet velocity is 320 meters per second. And that's got to be squared. The inlet velocity is 50 meters per second, yes. And that's got to be squared, okay? Now, one little thing before we proceed. When you have these kinetic energy calculations in the energy balance, the unit on enthalpy is usually kilojoules per kilogram. The unit on kinetic energy, it's going to be an energy per unit mass. This term here, this has units. This quantity here has units of meters squared per second squared. It's actually a joule per kilogram. If I multiply meters squared per second squared by a mass, I get a joule, which is a unit of energy. Think kinetic energy, 1/2 mv squared. If I have simply a velocity squared, I have a joule per kilogram. The unit on these kinetic energy terms, which is the velocity squared terms, has units of joule per kilogram, whereas the unit on the enthalpy, specific enthalpy, is kilojoule per kilogram. So when you do calculations involving kinetic energy, you need to convert the joule per kilogram into a kilojoule per kilogram, especially if you have an enthalpy or some kind of other property in the equation. So I'm going to, let's see, convert this into a kilojoule. So 1 kilojoule is equal to 1,000 joules. Okay? And so the joules will cancel out here, and I'll get kilojoule per kilogram. Kilojoule per kilogram. Let's see here. Let me crank out the specific enthalpy here. Let's crank out the specific enthalpy here. Let's see here, we have 320 squared minus 50 squared, divide by 2, divide by 1,000, and then 350 minus that is going to be our enthalpy. So I get 300.5 kilojoules per kilogram. My outlet specific enthalpy. My outlet specific enthalpy is 300.5 kilojoules per kilogram. So H2 is 300.5 kilojoule per kilogram. Now, if I go to a table, my air table, let's see if I can find the temperature associated with 300 kilojoules per kilogram. Let's see here, 300 degrees, 300 kilojoules per kilogram. I'd say the outlet temperature is about 300 degrees. By the way, for low temperatures, the specific enthalpy for air is approximately the same numerical value as the temperature in Kelvin. That works for low temperatures. If you go to higher temperatures, let's say 2,200 degrees Kelvin, the specific enthalpy is 2,500, not 22. So I'd rather you didn't use the rule of thumb to estimate H as a function of T by taking the same numerical value as temperature. I'd rather you actually came to the table and extracted out the proper specific enthalpy, okay? So we have an outlet temperature of 300 degrees Kelvin from tables. So T2 is 300 degrees Kelvin. And all this is from table, what is it? What's the air table? I don't know what it is. B11. B11. Okay? You could have also done this problem assuming constant specific heats. You would have had a delta H. Earlier in the energy balance, you had a delta H term, H2 minus H1. You could have substituted in Cp delta T. And if you assume constant specific heat, you do that, you can extract out T2 fairly quickly without using tables. All you need is a specific heat evaluated at some representative temperature, okay? So outlet temperature, 300 degrees Kelvin, okay? So we started off at 350. And the temperature goes down to 300 degrees. So temperature falled. Why? Why did it fall? Because we're converting internal energy and pressure power into kinetic energy. It cooled as it accelerated. Let's calculate the outlet flow area, A2. How large does this area have to be for the air to flow in and then flow out? Okay? Well, clearly this is a conservation of mass problem. So how do we know what area 2 is? How do we know the outlet area? So we're going to apply conservation of mass. We already did that, in fact, and we found out that the inlet flow and the outlet mass flow rate are the same. M dot 1 is equal to M dot 2 is equal to M dot. Okay, that was from the mass balance. So to get area 2, we apply the mass balance. And we found that M dot 1 is equal to M dot 2. Now, what's the mass flow rate at the inlet and the outlet? Well, the mass flow rate at the inlet, is equal to the density of the air at the inlet times the flow area times the velocity. You get the flow area times the velocity, you get a volume flow rate. meters per second times an area, that's cubic meters per second. So you get a volume flow rate, and you go from a volume flow rate to a mass flow rate with density. So m dot 1 is equal to the flow area A1, the density rho 1, and the velocity VEL1. Okay? So flow area times velocity times density, excuse me, looking good, gives you a mass flow rate. So this guy is A1, rho 1, VEL1. Mass flow rate at the outlet is going to be the flow area at the outlet times the density at the outlet times the velocity at the outlet. So let's write what I have. A1, inlet flow area, density at the inlet, times the velocity at the inlet is equal to the outlet flow area, density at the outlet, times the velocity at the outlet. Now, what are these densities? Well, if we use the ideal gas law, we're assuming IGB is valid. We're assuming IGB is valid. I can use the ideal gas law to calculate the densities. So from IGB, pressure times volume is equal to mRT. Density is mass divided by volume. So this implies density, which is mass divided by volume, is equal to pressure divided by RT. Pressure divided by RT. So that's density according to the ideal gas law. So this density here is actually pressure divided by RT evaluated at the inlet. This is pressure divided by RT evaluated at the, inlet. Pressure divided by RT evaluated at the outlet, okay? So let's make our substitution here. A1, pressure RT1, velocity 1 equals A2, pressure RT2, outlet velocity, okay? Via IGB, ideal gas. The gas constants cancel out, so we don't have to worry about plugging those in. That's nice. And I can do a little bit of algebra here, and let's solve for area 2. So area 2 is equal to area 1. And then I got P1 over P2. And then I have T2 over T1. And then I got some velocities. VEL at the inlet divided by VEL at the outlet, okay? Now, I know all these things. I know the pressures, I know the temperatures, I know velocity. Let's plug in. The inlet flow area. Inlet flow area, 1/100th of a square meter. Inlet pressure is 3 kPa, outlet pressure is 100 kPa. Inlet temperature is 350, outlet temperature is 300. Inlet velocity is 50 meters per second. Outlet velocity is 320 meters per second. We have everything. 0.01 square meters. Pressure ratio, 300 over 100 kPa. kPa's cancel out. Temperature, the outlet temperature is 300 Kelvin. The inlet temperature is 350 Kelvin. Kelvins cancel out. And then I've got the inlet velocity, which is 50 meters per second. and the outlet velocity, which is 320 meters per second. They cancel out, okay? Units cancel out. All that I have left over is meters squared, which is a unit of area. Let's see here. Let's crank this out. Let's crank out what this final area, flow area is. Hopefully it's smaller than the inlet flow area, else it wouldn't be a nozzle. Hopefully A2 is less than A1. Let's see here, 0.01 times 300 over 100, and then 350 divide by, 300 divide by 350. And then I have 50 divide by 320. And I get 0.004 meters squared. So the outlet flow area, A2, is 0.004 meters squared. Notice that is less than the inlet flow area, which is 1/100th of a square meter. So A2 is 0.004 meters squared, which is less than 0.01, okay? All right? Pretty straightforward, okay? Pretty straightforward. All right, let's go through and do another example here. Instead of having a air nozzle, we now have a steam turbine. Remember, a turbine produces power, or shaft power in particular. So it works off of steam, not air. So obviously we're going to be using steam tables and saturation tables to do this particular problem. So we have a steam turbine that takes high pressure steam. The inlet is location 1, the outlet is location 2. Of course, there's a propeller or a turbine in there that's extracting shaft power. The inlet pressure is 10 megapascals. And that turns out to be 100 bar. So the inlet pressure is 100 bar. P1 is 100 bar. Very high pressure, 100 atmospheres. The inlet temperature is T1 is 450 degrees C. Probably going to find that it's superheated, so probably going to be a superheated steam once we actually go to steam tables. The inlet velocity of the steam is 80 meters per second. And the mass flow rate for the steam, m dot, is 12 kilograms per second of steam being fed into the turbine. Now, the turbine extracts some energy from the flow, and as a result, our outlet pressure falls. P2 is down to 10 kilopascals, which is 0.1 bar. So pressure falls from 100 bar down to 0.1 bar. 1,000 times pressure has gone down. And we're also told that the exit state is a saturated mix. So we have a quality of 92%. So it's a saturated mix. A superheated steam condenses down to a saturated mix primarily of saturated vapor, but there's a bit of liquid in there, and pressure falls by a factor of 1,000. The outlet velocity, VEL2, goes down to 50 meters per second. Okay? Pressure, velocity, and we'll find out enthalpy have fallen because we're extracting energy from the flow to produce shaft power or shaft work. Okay? What are we supposed to find? We're going to find the change in specific kinetic energy from the inlet to the outlet. So delta KE from the inlet to the outlet. We want to find the shaft power, W dot shaft, produced by the turbine. And presumably, I also want to know what the inlet flow area is. So this thing some sort of a pipe here, some sort of pipe in which the steam flows in and the saturated mix flows out. I want to know what this flow area is here, A1. I want to know what that flow area is, all right? Okay, let's proceed. So the first thing I want to do is calculate analysis. First thing I want to do is calculate the change in specific kinetic energy between the inlet and the outlet. So delta KE from location 1 to location 2. So that's going to be 1/2 velocity at location 2 squared minus 1/2 velocity at location 1 squared. Let's group together the 1/2s. Factor out the 1/2 and I have velocity 2 squared minus velocity 1 squared. I have the inlet and the outlet velocities. They are 80 and 50 meters per second. So I got 1/2. The outlet is 50 and the inlet is 80. So I have 50 meters per second squared minus 80 meters per second squared. Okay, the unit on this is going to be meters squared per second squared, which is a joule per kilogram. Joule per kilogram. So these guys have units of joule per kilogram. Not kilojoules, joules per kilogram. Let's see, I go through and crank that out. 50 squared minus 80 squared. So kinetic energy is falling as we go from the inlet to the outlet. Let's see here. So 50 squared minus 80 squared, divide by 2. And I get 1950, negative 1950. And that's going to have unit of joule per kilogram, or converting that to kilojoules per kilogram. I got 1 kilojoule per 1,000 joules. The joules cancel out, and I get 1.95 kilojoule per kilogram. So I'll write that right up here. Delta KE from the inlet to the outlet is 1.95 kilojoule per kilogram. Okay, kilojoule per kilogram. There we go. That was easy. That's the easiest part of this problem. Well, yeah, definitely one of the easiest parts of the problem. All right. Okay, now I want to calculate the shaft power or power produced by this turbine. Well, first of all, let's define our system. Before we get too excited here, let me define my system here. Clearly an open system. I'm going to make the inside of my turbine the system. So the shaft is delivering shaft power by the system. It's out. It's producing work, so it's by the system. Clearly an open flow device with a single inlet at location 1 and a single outlet at location 2. Single inlet, single outlet, producing shaft work. One other little thing here. Well, we'll wait for the other little thing, okay? We'll wait for the other little thing. So let's write the energy balance. That involves shaft power. Let's write the energy balance and see if we can calculate the shaft power. So energy balance for an open system, Q dot minus W dot is equal to the time rate of change of energy within the turbine or the control volume plus the sum of M dot H plus PE plus KE summed over all outlets minus the same thing summed over all inlets. I'm not going to write it. It's the same thing, inlet, outlet. I'm getting tired of writing it, okay? Getting tired of writing it. You can write it down. m dot h plus PE plus KE, all right? Okay, let's whittle this down here. What do we do with the Q dot term, the heat transfer? It doesn't say it, but why don't we assume an adiabatic turbine? There's no way to calculate the heat transfer. I'm trying to calculate W dot. I'm going to end up with one equation and one unknown. I can't have two unknowns. So I'm going to assume Q dot is 0 or an adiabatic turbine. Adiabatic turbine. That's the first assumption I'm going to put down. So Q dot equals 0, adiabatic. Adiabatic turbine. I'm going to put some insulation around this thing. No heat transfer. Wrap it with some asbestos. Just don't breathe it, okay? Let's wrap it with an asbestos blanket. No heat transfer, all right? By the way, there's one of these over in the power plant. It's being dismantled now. It's not actually installed. The power plant is not generating any electricity at this moment. But usually, there's a turbine running over there in the power plant driving a generator, which is helping to power the lights. Okay, so there's one of these guys in the power plant, steam turbine. No heat transfer, so that's gone. Adiabatic. Now, what about the W dot term? There are three forms of work that we're dealing with here in the energy equation. Pressure power is absorbed into the enthalpy, so we don't have to worry about that. There's shaft work, electric work, and boundary work. I definitely see a shaft in this thing, so we definitely have shaft work going on. I don't see any wires. I don't see any resistors, any wires, any batteries, so there's no electric work. And I'm guessing, I'm assuming that the turbine itself is not changing shape. The casing is remaining intact, and the control volume is not changing its volume, getting bigger, being distorted. So I'm going to assume that the work is equal to, I'm going to write right here, W dot is equal to W dot shaft. Okay? No boundary, no electric work. So I'm immediately going to substitute W dot shaft. W dot shaft, all right? I'm going to neglect the change in internal energy. I'm going to assume steady state. So I can get rid of dECV dt, get rid of that. Steady state. So get rid of the time rate of change of the energy within the control volume. I'm also going to neglect the change of potential energy of the steam as it flows in and out of the turbine. I have no way to figure out what the average height is for the inlet and the outlet steam. Okay, maybe there's no change in height. I don't know, depending on how the plumbing is done. Certainly, steam is not very dense. It has a very low density. So even if there was a change in height, it would have to be very large to be comparable to the change in enthalpy or kinetic energy of the flow. So I'm going to neglect, I'm going to write delta PE from 1 to 2 equals 0. I'm going to neglect the change in potential energy of the steam as it moves through the turbine. So I'm going to cancel out these potential energy terms. Okay, cancel out the potential energy terms. Well, let's write what I got left. By the way, there's one inlet, one outlet. So the summations go away. So let me write what I have left over. Minus W dot shaft, minus sign, is equal to M dot out, which is M dot 2, H plus KE at the outlet, minus M dot H plus KE at the inlet. If I apply the mass balance to my turbine, single inlet, single outlet, single inlet, single outlet, steady state, no change in mass within my turbine. If I apply the mass balance, what's the relationship between M dot in and M dot out? M dot in and M dot out are the same. What goes in has to go out in steady state. Single inlet, single outlet. So I'm going to replace the m dot 1 and the m dot 2 with a single generic m dot. So this guy here is just m dot. If you want to prove that, you can go through the mass balance. You're going to see that. M dot 1 is equal to m dot 2. And I'm just going to call them m dot. Okay, let me group together the enthalpy term and the change in kinetic energy term, and I'll have my final version. And I'll also distribute the negative sign. How about that? W dot shaft, I'll distribute the negative sign, is negative m dot delta H. How about H2 minus H1 minus, tell you what, H2 minus H1 plus KE2 minus KE1, okay? Where this guy here, that is delta kinetic energy from 1 to 2. We've already calculated it, all right? So let's write out the final version. W dot shaft is equal to minus m dot H2 minus H1 plus delta KE from 1 to 2, okay? We've already got this. By the way, we have the mass flow too. We have the mass flow too. Okay, now we need to find the specific enthalpies at the inlet and the outlet. Define the specific enthalpies at the inlet and the outlet. Well, let's find the specific enthalpy at the inlet. H1 equals specific enthalpy of the steam evaluated at a temperature of 450 degrees C and a pressure equal to 100 bar. Let's see if we can find this temperature and pressure. Maybe we'll have to interpolate, but let's see if we can find something in the steam tables. Let's see here. Whoops. Superheated, R1, no, don't need that. H2O, 100 bar, 450 degrees C. Ooh, looks like we need to do, so here's H. We're at 450, so we have to interpolate between these two. If you go through and do a little interpolation, hopefully I have it here. I have H1 is 3240.25 kilojoules per kilogram. 3240 kilojoule per kilogram. And that's from the steam tables, and you have to interpolate. That's from the steam table B4, and you have to interpolate. B4 interp. I had to interpolate from B4, okay? That's H1. What about H2? H2 is a saturated mixture. I have a pressure P2 is equal to 0.1 bar, and a quality X2 is 92%. So we'll have to go to saturation tables. Saturation pressure table, 0.1 bar. Here is H for the saturated liquid. Here's HFG, which is the enthalpy change between the vapor and the liquid. Use the quality, you can quite easily calculate H2. I won't bore you with the calculation here, I'm just going to put the value down. Let's see here, H2 is 23 93.2 kilojoule per kilogram. I'll get rid of the 0.2. 2393 kilojoule per kilogram. Okay, now I have all these specific enthalpies. Let's crank out the shaft power. Let's see here. M dot was 12 kilograms per second. H2, 2393. H1, 3240. And those both have units of kilojoule per kilogram. And then I have my delta KE from 1 to 2, which is 1 point. I should have a negative sign there. Kinetic energy falls. I just realized that. I dropped the negative sign, okay? Delta KE from 1 to 2 is negative because velocity going in is 80, velocity going out is 50 meters per second. So kinetic energy falls, so I got a negative 1.95 kilojoule per kilogram. Looks like I dropped the negative sign. So negative 1.95 kilojoule per kilogram. All the units are the same. Looks good. By the way, the kilograms cancel out with the kilogram and the m dot, and I get kilojoule per second, which is going to be a kilowatt. Kilojoule per second is going to be a kilowatt. Let's see here. So I have 2393 minus 3240 minus 1.95. I'm going to multiply that by 12. And I get 10,187.4 kilowatts. I'm going to convert that into megawatts. Let's see, a megawatt, running out of space here. 1 megawatt is equal to 1,000 kilowatts. So the kilowatts cancel, and I got to divide that by 1,000. And I get 10.18 megawatts. So the shaft work supplied by the turbine is basically 10.2 megawatts. 10.2 megawatts. That's how much power is being produced by this thing. Oh, shoot. Okay, well, at least you could see part of the screen. All I did is plugged in the specific enthalpies, cranked it out. Again, the negative sign on the delta KE. Potential energy falls as you go from the inlet to the outlet. Okay, so I forgot the negative sign there. 10.2 megawatts. That's a lot. That's a lot of power. A lot of power. A lot of light bulbs. A lot of light bulbs if you turn that into electric power. Okay, last thing we need to do is calculate the inlet flow area. Inlet flow area, A1. Inlet flow area. So we have the inlet here. So we got m dot for the steam. Okay? And of course, this inlet has some area, A1. Okay? So, m dot for the steam is going to be equal to the volume flow rate at the inlet times the density of the steam at the inlet. So V dot rho 1. Now V dot, that's equal to the velocity at the inlet times the flow area at the inlet. Okay? And density is 1 over specific volume. So this guy is 1 over specific volume at the inlet. Tables don't give you density, they give you specific volume. That's why I'm converting density into specific volume. So I have velocity 1, area 1, over specific volume at the inlet. Okay? Now the inlet area is what I want, A1. So let me solve for the inlet flow area. A1 is equal to m dot steam, or m dot, just m dot. Specific volume at the inlet divided by the flow velocity at the inlet. Okay? Now I have the steam flow rate, which is just my m dot, and I have the inlet velocity, which is 80 meters per second. I don't have the specific volume at state 1 for my superheated steam. Let's see here, how might I get this? Specific volume at state 1 is specific volume for the superheated steam evaluated at 100 bar and 450 degrees. So 100 bar and 450 degrees C. I'm going to have to do some interpolation on that too. If we go to our tables, as I recall, we don't have, so let's, whoops. Let's go to the steam tables. 100 bar. And again, I don't have 350, 450. I have 440 and 480. So you have to do some interpolation here. It's going to be somewhere around 0.03 or so, 0.03 cubic meters per kilogram. Okay, do a little bit of interpolation. Do a little bit of interpolation here. I have 0.0297 cubic meters per kilogram, and that is interpolated from B5 in terp. Is it B5? And I've done it again. I'm sorry, B4. Okay, so I interpolated the specific volume. That's from B4 in terp, interpolated. Okay. Okay, I've got everything. I've got the velocity. I've got the specific volume. Oh, let's see here, 12 kilograms per second. Again, this is just m dot. I don't know why I'm writing m dot steam. 0.0297, not 9. I don't know why I put the 7 there either. Okay, 0.0297 cubic meters per kilogram. And the inlet flow velocity is 80 meters per second. Let's see here, let's look at the units here. The seconds cancel out, meters per second and kilograms per second, that's gone. The kilogram cancels out in the mass flow and the specific volume. And one of the meters cancels out in my cubic meter per kilogram, and I get meters squared. I get meters squared. The result is 0.004 square meters. So the inlet flow area. Inlet flow area is 0.004 square meters. If we want to change this into centimeters, maybe a little bit more visualizable, there is 100 centimeters per meter. And I'm going to square the conversion, so I get meters squared and centimeters squared. The meters squared cancels out. And I get, okay, I'll move the decimal place over 4 times. 1, 2, 3, 4. So I get 40 centimeters squared, okay? 40 centimeters squared, or 0.004 square meters, okay? That's the outlet flow area. That's all I have for today, ladies and gentlemen. We'll finish up the chapter on energy. We'll introduce what's called coefficients of performance and efficiency. We'll wrap up chapter 4, and then we'll be moving on to the most troublesome part of the whole course, the second law and entropy. Get a good rest up this weekend, get your homework done, get everything else done, because now it's going to start getting nasty. going to be horrible. You're going to be, who knows, you might be in the hospital after this is all done. Second law on entropy tends to explode people's brains. So this stuff, pretty straightforward. I hope you're getting it. I hope you're used to the tables. I hope you can find properties for steam and air. Let's get this stuff down. Do the next homework involving the energy balance. Get it down. Then we're moving on to the second law of thermodynamics, and then entropy. Entropy. Take care, ladies and gentlemen.